Here we see a long uniform beam hinged to a wall at the left with a cable attached at an angle of 23 degrees at a distance of 3.4 meters from the wall. Hanging from the end of the beam is a 720 Newton weight. And the idea is to figure out what the tension in the wire is. Now the beam is clearly not moving. It's not rotating because it's being held up by the tension in the cable, and it's not accelerating horizontally or vertically. So there's two conditions for equilibrium in this case. One is that the net force is zero, and the other is that the net torque is zero because it's not rotating. Now we know that when F net is zero, that's the condition for translational equilibrium. It simply means that the object is not accelerating. We also know that when the torque is zero, the object is not rotating, so therefore it's in rotational equilibrium. When all are true, in other words, the object is not moving at all, we call that static equilibrium. Now let's see how we're going to go about solving this question. The question wants us to determine what the force is acting on the cable. Now there's lots of ways to solve these things, but I always like to simplify it. And the item that's in equilibrium, the item in question here, is the beam. It's not the hanging mass. We know that the hanging mass is in translational equilibrium. That's simple. If there's 720 newtons down, there has to be 720 newtons up. The beam is the elongated object that we has to satisfy both translational equilibrium and rotational equilibrium. So what I want to do is draw the beam one more time as simple as possible and label just the forces acting on the beam. Let's do that now. Okay, so let's label our forces as we see them. There's the force on the far right, the 720 Newton force. That's acting straight down on the beam. Now remember, we're only worried about forces acting on the beam. So let's first label the 720 Newton force, and we know it's straight down. So it's going to act on the end of the beam at the right. The next force is the weight of the beam itself. Now it tells us that the beam weighs 425 newtons and that the beam is uniform. So there's no thick or thin spots. It's a nice, steady, consistent density all the way throughout. And we already know that all the weight of that uniform object will be concentrated right in the center. So we can label that 425 Newton force as if it all acts in the direct center of the beam. So let's do that now. And our last force, of course, is our tension force acting on the cable. Now it's acting upward at an angle of 23 degrees, something like that, 3.4 meters from the end. Now there's actually two more forces present. The hinge itself is exerting some forces. You can see that the cable, the blue force that I've drawn here, is pulling both upwards and to the left. And since we know the beam is not moving, there must be an equal and opposite force to the right acting on the beam. Let's put that in. Now we'll simply call this force, because it's acting in the horizontal direction, we'll call it Fx. We don't know what the value of it is. We could probably figure it out later. There's also a y force. Now we don't know if the y force is going to be up or down. It depends on which is winning. The 720 and the 425 are acting down, and there's a y component of the tension acting up. But we need to recognize that it's there. So we're just going to guess that it's upwards to assist the cable. So we'll just call this force Fy. So there's our simplified diagram. I've chosen my pivot point at location P at the end. That way the torques generated by Fy and Fx are zero because the distance to the pivot point is zero, and I've effectively eliminated two unknowns from my rotational equilibrium condition. So I choose the pivot point to eliminate unknowns. Now the condition for equilibrium, for rotational equilibrium, is that the sum of all the torques has to add up to zero. In this case, if this is my pivot point, in other words, I drive a nail through the board and these are strings acting on that board, my two red forces, F1 and F2, are causing the beam to rotate clockwise. And let's say clockwise is positive. So F1 and F2 are going to generate positive torques, and Ft is going to generate a negative torque. So our equation is going to look like this. So in my equation, T1 is the torque generated by F1, T2 is the torque generated by F2, and capital T tension, is the torque generated by Ft, the tension force. Notice this one's negative because we said it's counterclockwise. Now torque 1 is force 1 times the distance to the pivot point. Force 1 is the weight of the beam. It's right in the dead center of the beam. And if the beam is 8.4 meters long, the dead center will be at 4.2 meters. So torque 1 will be 425 times 4.2. Let's put that one in right away. Force times distance. Torque 1 will be 425 newtons times 4.2 meters. Now remember, with torques, the force and the distance have to be 90 degrees to each other. So if I'm using a distance of 4.2 meters along the beam, that force has to be at right angles to that distance, and it already is. So we're good to go with that one. Similarly with F2, the 720 Newton force and the distance to the pivot point are at right angles to each other, so I can put them in directly. So I've got 720 newtons of force acting at a distance of 8.4 meters from the pivot point. Now the last one, our tension force. Our tension force acts at a distance of 3.4 meters from the hinge. So we know the distance, but if you look at the diagram, this tension force is clearly not 90 degrees to that 3.4. I'm going to need to use a component of the tension force to determine this. So what I'm going to do is write that as Ft perpendicular. So when I write my tension force, it's going to look like this. Let's move things over a little bit. Minus Ft perpendicular times 3.4 meters. And remember, all of that has to equal 0. I'm going to put it over here because I've run out of space. So all of this equation has to add up to 0 for the torques to be balanced. So the only thing left now is to solve for Ft perpendicular. I'm going to label that on my diagram just so I remember what I'm actually solving for. Now you can see on the diagram I've labeled that Ft, and I've labeled it to look like Ft perpendicular. So that's what we're going to look for, this green dotted line. That's what we're trying to solve for. So when I work this equation out, I get Ft perpendicular is 2,304 newtons. Now that doesn't answer my question. I want to know what the tension is in the cable, not the perpendicular component. So I now know this piece. It's 2,304. And now it's just a matter of solving for the hypotenuse of that triangle. This little angle right here is labeled already. It's 23 degrees. So it would be easy enough to figure out that this top little angle, the one between Ft and my blue line, is going to be 67 degrees. And all we have to do now is find the hypotenuse of that triangle. So we have the adjacent side and we're trying to find the hypotenuse, so I'm going to use cos. Let's slide things up so I have a little bit of room. So I'm going to say cos 67 is adjacent over hypotenuse, and it's the hypotenuse we're looking for. What is the actual value of Ft? And when I solve for this, I should get an answer that's bigger than 2304, 5,896 newtons, or 5,900 newtons.